I'm sharing the screen. Okay, 1 second. Yeah, sharing. Okay. Yeah. So in this first so whatever the codes I shared, that only I'm going to discuss today. Okay. Yeah. My ASIC. This Verilog codes are there, no? In this Verilog codes, there's level 0, level 1, level 2 are there. So in level 0, I want to discuss about the logic gates behavioral modeling. Okay, the logic gates behavioral modeling. Okay, so if you see the logic gates behavioral modeling, my screen is visible now. Yeah, so logic gates behavioral modeling. This is logic. Okay, so if you see the program, just yeah. So I'm expanding this. Yeah. So SC serial number. Okay, module logic. I'm initializing the port list A comma B comma Y. Input A comma B. Input I'm initializing with A comma B. So when you are using behavioral modeling, you need to use the output with reg data type. Output reg 7 down to 0 Y. Okay, 7 inputs and outputs are there. Always at the rate A comma B. Begin if A equal to 1 B and B equal to 1. So y equal to and operation. Okay, this is I am doing with and operation. Okay, so that is y of 0 equal to what 1, else begin y of 0 equal to 0. Okay, this is for and operation. Okay, if A equal to 1 and B equal to 0, A equal to 1 and B equal to 0. Okay, here this you need to do R operation. Okay, not and operation. Okay, and this is OR operation. OR means need to get. Okay. So it is doing if A equal to 1 or B equal to 0, y of 1 equal to, you are getting OR operation. Okay, I am doing OR operation. Else if A equal to 1, B equal to 1, y of 1 equal to 1, or else if A equal to 0, B equal, based on the truth table only I am writing. Okay, based on the truth table only 0 1. Okay, y of 1 equal to 1, else y of 1 equal to 0. Okay, and not operation. So if A equal to 1, not, so that means A equal to 1, y of 2 equal to 0. Okay, else y of 2 equal to 1. Okay, this is not operation. Okay, from here to here this is not operation. And if A equal to 1, buffer y of 3 equal to what, buffer 1, else y of 3 equal to 0. Okay, similarly XOR operation. XOR operation means what? If A equal to 1 and B equal to 0, y of 4 equal to 1, else y of, if A equal to 0, B equal to 1, y of 4 equal to 1, else y of 4 equal to 0. Okay, just I am verifying the truth table only. Okay, NAND operation. This is NAND operation. So if A equal to 1, B equal to 1, y of 5 equal to 1, else y of 5 equal to 1. If A equal to 1, B equal to 1, y of 6 equal to 1, else if A equal to 1, B equal to 0, y of 6 equal to 0, else if A equal to 0, B equal to 1, y of 6 equal to 0. This is for NAND operation. Just you draw the truth table and you verify this one. Okay, similarly this is for NOR operation. NOR operation, so y of 6 equal to 1, if A equal to 0, B equal to 1, y of 7 equal to 0, if else if A equal to 1, B equal to 0, y of 7 equal to 0, else if y of 7 equal to 1, end and end module. Okay, so that means you need to use a procedural blocks when you are using the behavioral modeling. So you need to use the initial and always. Initial is non-synthesizable, so we can't use in the RTL code. We need to use always block only. Always block at the rate, this is nothing but sensitivity list. Sensitivity list is nothing but whenever there is a change in the input, there is a change in the output. That is nothing but sensitivity list. Okay, so this one, just go to Vivado and create the new project, new. Okay, create next. So here I am creating the new project. Okay, so project name is combinational underscore behavioral modeling. No, BHM I am using. Okay, BHM, behavioral modeling, BHM. And so I need to select the folder. So which folder here I'm using so ASIC offline Verilog programs Verilog programs I'm using. Okay, Verilog programs only. Okay, this Verilog programs. Okay, this file I'm using. Okay, Verilog programs, and next there the project will be created. RTL project. Create the file name. Okay, what is my file name? My logic. Whatever the module name is there, that same module name I need to initialize. Okay, with this one. Okay, so copy this and just paste in this. Okay, logic. Next, this is the optional only. Next, finish. Okay, yes, I want to close this. Yeah, my module name is also logic. Yes, my module name is also logic. It is created. Okay, so just here you copy this code for checking the all the logics. Okay, so just copy and paste in this. Okay, so save this logic.v. Logic.v is saved. I want to see the so test bench is not completed, that's why I want to see the elaboration only. Okay, elaborate the design. Yeah, so it is looking like if else statement we are using means it is taking like a mux only. Means what, if this one is there, that one is selected, and this one is there, that one is selected. So if else statement means mux will be taken. Okay, mux will be taken, and you are getting like this. Okay, so this is the basic logic gates, and next program we'll see. Next program, half adder, logic gates, mux, data flow, full adder. Full adder, full adder means first you need to write the half adder code, then you can write the structural modeling. With this one we already discussed. Structural modeling is nothing but instantiation. Okay, first you need to write for the half adder, and you need to instantiate by half adder by 2 times, and one OR gate you need to use. This is nothing but normal my structural modeling for full adder. Okay, and coming to this data flow, behavioral, yeah, logic gates, behavioral is there. Mux, mux code you see, 2x1 mux module. This is the data flow only. Okay, you can try this data flow modeling. Okay, logic gates, data flow, logic gate behavioral already completed. Okay, encoders, if you see the encoders, it's not there. 328 encoder. Level 1 we'll see. So level 1, 4-bit adder subtractor. 4-bit adder subtractor, if you see. So this is adder subtractor. So first I need to write the program for full adder, and I need to instantiate for, so see here, this is adder subtractor code. I think this I told, I think so. Adder subtractor code I told. Okay. Carry look at adder, and this is OR gate by using 2x1 mux. This is OR gate by using 2x1 mux. Okay, so here this is also behavioral modeling. Okay, see here. So if you see OR gate using 2x1 mux, so how to design the OR gate by using 2x1 mux? Did you remember how to design the OR gate by using 2x1 mux? Any idea? OR gate by using 2x1 mux. Here based on the truth table only, in digital I told you, no. So based on the truth table only we need to design. Okay, so normally like open the one PPT. Give me 1 second. Yeah. Yeah. So this one I'll open. Insert slide 0. Okay. So R gate using 2x1 mux means here R gate using 2x1 mux. How to design? So here if you see R gate using 2x1 mux. So if you see the 2x1 mux, so normally first you write the truth table for R gate A, B, and output is what? Y. Output is Y. Okay, 0 0 0 1 1 0 and 1 1. Okay, so this is what? 0 1 1 1. Okay, this is the truth table for OR gate. So you need to divide. Here output is following. So here this is I naught. I naught equal to what? I naught equal to B. Okay, it is following. And here I1 equal to what? 1. Okay, A is the selection line. Why? Because here 0 and here 1 is there. So that means here you need to draw. Okay, so this is 2x1 mux, 2x1 mux, and this is B, and this one is 1. Okay, this is output is Y, and the selection line is A. Okay, so if you write the Shannon's equation, what you are getting? A bar and B plus A and 1. Okay, so that means here A plus A bar B. So you are getting, by using absorption law, you are getting A R B. Okay, so this is the OR gate using 2x1 mux. Okay, so here if you see the Verilog code, OR gate module R underscore DOT, and what are the inputs? I0, I1 and selection. Output you need to initialize with reg z, always at the rate star. Star is nothing but implication operator. Suppose your input is having 100 inputs or 150 inputs, so in the sensitivity list it's impossible to indicate all the inputs, so you can use the implication operator, that is star. So when you are including this, so that will be available, means if there any change in the input, then there is a change in the output. Okay, it will be applicable for all the inputs. Okay, begin case select. So one tick binary equal to I0, one tick binary 1 equal to I1, default Z equal to I0, end case and end module. Okay, this is RDUT. 1 second. RDUT run file. Okay, so okay, yeah, this is R gate. So just I want to execute this. So just copy this. So here RDUT is there, no? So this RDUT, just copy this, and in the Vivado, so close this elaboration. Okay, close this elaboration and add the file. Okay, add the file and create the design source. Create file, create my file RDUT. Okay, finish. My file name, module name is also RDUT. Okay, and here just yeah, I delete this. So say, copy this one, paste in here. So save this and elaborate the design. Okay, I will want to see how the circuit will look like. Yeah, means here I need to make this as top module. Okay, when you
Yes, sir.
when you are elaborating the design, you need to set as top module. Yeah, top module, and elaborate the design. Yeah, you got normal mux only. This is not R gate using mux. Normal 2 cross 1 mux by using behavioral modeling only. Okay. So if you want mux means here you need to change. Okay. Here you need to change. That means in the diagram, what you got? One second. In the diagram, where is my PPT? Yeah. So see here, I not equal to b and I1 equal to 1 you need to give. Okay. So in this I need to give one tick binary 0. Okay. This one I need to give it to this is input input. Let us take the inputs are what, a comma b.
B.
A is the selection line, no? A comma b only we need to give. Okay. A comma b we need to give a comma and b. Okay. And semicolon and reg z and a comma b, a comma b, selection you are using, no? Okay. Selection is a, selection is
సార్
a.
ఇన్పుట్లో
What
ఇన్పుట్లో సెలక్షన్ అని అవ్వాలి కదా సార్?
input selection, input only selection line is a,
ఓకే
no?
ఓకే సార్, ఓకే సార్, ఓకే సార్.
Selection line is a, no? So
ఏ
case a, input a comma b, z
Sir,
equal to
there is a
what?
no. Sir, two inputs, no, sir.
Two inputs.
A
Okay.
is the selection line, B is the input, and one is also an input now.
One is also input. How we can declare input? Okay. Directly I will give one tick binary 1. Set input a comma b, selection. This you try here. Okay. Any doubt is there? I will. This is normal mux only, but we need to try this. We need to implement all the gates by using 2 cross 1 mux by using behavioral modeling. Okay. This you try and come up with the solutions. Okay. Yeah. Next, if you see the XOR gate by using 2 cross 1 mux, XOR gate DUT. Here also same thing you wrote. Means in the test bench I think we need to see the test bench. If it is test bench means yeah, in the test bench he wrote like that. Okay. Normally design we wrote a normal 2 cross 1 mux only, but in the test bench we are instantiating that XOR gate. Okay. So normally in the design we wrote normally with 2 cross 1 mux only. Okay. That is 2 cross 1 mux. And encoder this is data flow modeling you can try. And level 2 will go to flip-flops. Flip-flops we'll see. Flip-flops, D flip-flop we are writing with behavioral modeling. Yeah, if you see the D flip-flop, okay. So if you see the D flip-flop, so you already know D flip-flop, okay. So module D flip-flop, D clock reset Q bar, okay. Input D clock reset, output reg Q bar, always at the rate passage of clock. Always at the rate passage of clock means what? This is synchronous synchronous reset we are using. Synchronous active low reset we are using. Okay. Begin, if reset equal to 0, begin, Q is initialized to 0, Q bar equal to 1. That means if reset equal to 0, you are initializing, begin, Q equal to 0, Q bar equal to 1. Else if D equal to 0, okay, begin, Q equal to 0 or Q equal to 1, and else begin, or otherwise I will show you one more program with the D flip-flop. It will be clear, I think so. One second. Yeah, D flip-flops I will show you. RTL codes, D flip-flop. This is D flip-flop. Okay, so if you see the D flip-flop, there are synchronous reset and asynchronous reset is there. Okay, this is nothing but synchronous reset. Okay, so if you see the D flip-flop, so module D flip-flop asynchronous reset, input wire clock, input wire reset underscore n. This is active low asynchronous reset. Okay, input wire D and output reg. I need to initialize reg Q. Okay, always at the rate passage of clock or engage of reset. This is nothing but asynchronous active low reset. Asynchronous active low reset. Begin if not of reset. Okay, Q equal to what? 1 tick binary 0. Else Q equal to what? D. Okay, if not of, if reset equal to 0, Q equal to what? 1 tick binary. You are resetting the output. Okay, else Q equal to D, end and end module. Did you understood this code? D flip flop. Shall I move forward? Hello.
Yes, sir.
Okay, see here. This is asynchronous active low reset. So here
Sir, voice not visible, sir.
voice is not coming up. Now is it fine? Now is it fine? Hello.
Yes, sir.
Now is it fine? No.
Yeah.
Yeah. So see here. This is normally my D flip flop. So what is this? This one. D flip flop asynchronous active low reset. Okay. So just copy this. Okay. In the Vivado, you create one more project. That project is related to what? So new project. Next, that project name is sequential circuit underscore BHM. Sequential circuits. Okay, circuits. Okay, sequential underscore BHM. Sequential underscore behavioral model. BHM is nothing but behavioral modeling. Okay, so you create one more project and create your file. Okay, what is my file name? D flip flop asynchronous reset. Okay, copy this. One second. Escape U. I'll open that code. Yeah, this code. Okay, this code I wrote in GVim. Copy this, and first I need to copy this module name. Okay, copy this and paste here. Okay, next. Next, this is optional only. Next, finish. Yeah, I want to close. Okay, save. Yeah, the module name is same. Yeah, see here. Here I am writing the code. What is my code? This code. Copy this and paste here. Okay, paste here. Save. This one is not required. Just elaborate the design. This is asynchronous active low reset. Okay, for the D flip flop, asynchronous active low reset. Yeah, see here how the circuit is coming. This is my elaborate design. Means there is a D flip flop and there is a clock and this reset underscore n is there. No, that is given to what? Clear. This is given to clear and this is Q. So this is how the compiler is converting your hardware. Understood? Asynchronous active low reset. Directly bubble is there. Why? Because when reset equal to 0, this will be activated. When reset equal to 1, this will be when reset equal to 0, that is it is there in reset mode. When reset equal to 1, it will be in the functional mode. Okay. Suppose did you understood any doubts or queries in this? Shall I move forward?
Sir, code once.
Yeah, code. Okay. Code I need to explain. I need to explain code once.
Yes, sir.
Okay, you see here. So if you see here, so module and this D flip flop. So this is D flip flop asynchronous underscore reset underscore read. This is my module name. Okay. After that, input wire. So wire I need to declare input wire clock, input wire reset underscore n, input wire D. Okay. Output, if we are using behavioral modeling, that to procedural block, that is always block when you are using. Output you need to initialize with rich data type. Port rule connections we already seen, no? So when you are using in the behavioral modeling, you need to use rich data type. So output rich q. Okay. So always at the rate passage of clock or negate of reset begin if not of reset. Means what? Passage of either it is passage of clock or negate of reset. Means active low. Okay, active low. If
Sir, we can only one now, sir.
what
Passage of clock or negate of reset.
or means what means when you I'll show you after test bench. I'll show you the D flip flop for the test bench in the asynchronous active low reset. Reset removal is synchronous with the clock. Reset applied is asynchronous with the clock. Okay, na? So that means when it is going from reset mode to functional mode, that is asynchronous with the clock. Okay, either or means what? Either it may be passage of clock or negate of reset. Understood? Negate means what? When it is going from 1 to 0.
Yes, sir.
Okay. If not of reset means what? If reset equal to what? 0. You need to reset the output. You need to reset the output. 1 tick binary 0. Else means reset equal to 1. Q is initialized to what? D. Q is initialized to D. End and end module. Did you understood the code?
Okay, sir.
Okay. Suppose asynchronous here here I'm using this is I'm copying this. Okay, I will add one more file, create and copy this. This is normal passage of reset. I will okay, passage of reset. Okay, finish, yes. So in the same code, just this one I am copying. So Control C, and in this I am giving what is this asynchronous. So this reset I given, and my module name is reset, and here so here I am giving passage of reset, passage of reset I am giving. Okay, passage of reset, and if reset okay, if reset passage of reset. Okay, so passage of reset, so that means always at the rate passage of clock or passage of reset. This is asynchronous active high reset. What is this? Active high reset. Okay, so active high reset, both reset applied and reset removal both are synchronous with the clock only. Okay, for this. Okay, so if reset equal to 1, I'm doing, I'm making the output to 0, or if reset equal to 0, I'm making it is in functional mode. Actually it is when reset equal to 1, it will be in which mode? Reset mode. Okay, it will be in reset mode. Okay, and when it this one, it will be in functional mode. It will be in functional mode. functional mode. Okay, for when reset equal to, if reset means what? Reset equal to 1, it will be in which mode? Reset mode. Else if reset equal to 0, it will be in which mode? Functional mode. Okay, so end. Do you understood this program? Always at the rate passage of clock or passage of reset. Okay, if reset equal to what? 1, it will be in which mode? Reset mode. Okay, else if reset equal to 0, it will be in functional mode. Okay, so just set a stop module, and I'm just you want to see the differences. Okay, so if you elaborate the design, how the design will look like. So just to write the code and just see the elaborated design only. Okay, don't go for simulation. Why? Because we not yet completed the test bench, that's why. So when we complete the test bench, when we discuss the D flip-flop, we will discuss in detail. Have you seen the difference in the previous and this one? When reset equal to bubble is not there. Yes, bubble is not there. So when reset equal to what? Reset equal to 0, it will be in which mode? Reset equal to 0, it will be in so reset is equal to 0, it will be in
Reset mode.
Reset mode. When reset equal to 1, it will be in which mode? Functional mode. Okay, so directly I am giving through the D flip flop. Okay, so this is asynchronous active high reset. Okay, did you understood? Shall I move forward?
Yes, sir.
Next, this program is there, synchronous. Okay, this is nothing but synchronous. This is active low reset. Okay, synchronous active low reset. Module D flip flop synchronous reset underscore n. Input wire clock, input wire reset underscore n. This is a terminology. Like when you are using active low reset, you need to indicate like this: reset underscore n. Input wire D, output reg Q. So as this is a behavioral modeling, output separately you need to initialize with reg Q. Always at the rate passage of clock. So for the synchronous reset, there is no other reset is there. So synchronous reset, only passage of clock is there. Okay, so both are synchronous with the clock only. Okay, if not of reset, Q equal to what? 1 tick binary 0, else Q equal to D, end and end module. Okay, so this is what, when reset equal to 0, it will be in reset mode, else if reset equal to 1, it will be in the functional mode. Okay, so this is there in reset mode. Okay, so terminology will apply. Reset is asserted. Okay, so this is reset is reasserted. That means this is in functional mode. This is in functional mode. Okay, so just you see the elaborated design. Just to copy this, and here you add one more module. For adding this, you need to add one more module and create the create the design source, create the file. So this is D flip flop synchronous reset underscore n. Okay, finish. Okay, yes. Okay, reset synchronous. This is my file. Okay, so go to this, copy this, and paste in this. Just to see the elaborated design only. Yeah, paste. Once again. Copy this and paste here. Yeah, main module is not there. Yeah, so save this. If I want to see the design, you need to make set as stop. So D flip flop synchronous reset underscore n, set as stop. Okay, it will be set as stop, and next elaborate the design. yeah, how you got synchronous reset? There is a D flip flop clock, and you are getting like through the 2 cross 1 mux you are getting. Okay, so when reset equal to 0, which one is connected? 0 is connected to the D flip flop. That means that is connected to D. Okay, that is connected to reset. Clear? Okay, and when reset equal to 1, it will be in functional mode. Okay, D is connected. Okay, so I will show you how it will be there. Just I will show you. See here, I am adding the slide. You can see in the elaborated design. First, this is one important question. Okay, so how many resets are there? How many resets are there? Tell me. One is asynchronous,
Synchronous.
and synchronous. Okay, asynchronous and synchronous. Again, in this you have two types: active low,
To have
and active high.
Active high.
Active high. Okay, and here also synchronous. So synchronous, active low, and active high. Okay, so if it is first asynchronous, active low is there. Active low, D flip flop if you take. So how the circuit will look like means, this is my D flip flop, D and Q. Okay, and this is the input. Okay, D and Q, and here this is Q bar only. So here this is the clock, and this is coming like this. Reset underscore n. This is given to which one? Clear. This is given to clear. This is asynchronous active low D flip flop. Okay, and coming to asynchronous active high. If it is asynchronous active high reset, so it will be like this. So this is clock only. Okay, this is clock and D. Okay, so passage of clock only I am writing. This is passage of clock, and this is clock, and this is D, and directly this reset is connected like this. Reset is connected to the clear signal. Okay, this is the hardware for asynchronous active high reset. Okay, coming to the synchronous. Okay, I will add the slide. 1 second. Yeah. Okay, so yeah, asynchronous. Now synchronous active low reset. Okay, synchronous active low reset means how it will look like. So here if you see, synchronous active low reset means here this is my D flip flop, clock is there. Okay, this is my clock, and this is D input. Okay, here you are connecting 2 cross 1 mux. Okay, so 2 cross 1 mux, here you are giving reset underscore n. Okay, so 1 tick binary 0, this is given to D input, output is given to D input. Okay, and here this D input is given here. Okay, not here, D input is given here. Okay, so that means when reset equal to 0, the output will be what? Q equal to what? So 0 will be connected. Through this 2 cross 1 mux. Okay, 2 cross 1 mux. Okay, and when reset equal to 1, it will be functional mode. D is connected to this D flip flop. Okay, and coming to the synchronous active high reset. Synchronous active high reset means what? So this is my D flip flop. And here you need to connect 2 cross 1 mux. So 2 cross 1 mux need to connect, and here this is reset pin is there. Okay, so when reset equal to what, active high, no, so here you need to connect one tick binary 0, and here you need to connect D, and this is given to this input, T input, and clock is there, and this is nothing but Q. Okay, so when reset equal to 0, it will be in which mode? Means functional mode. D input is connected. Okay, when reset equal to 1 means here you need to connect to 0 and 1. Okay, here also 0 and 1. Okay, I0 and I1. Okay, so when it is connected to 1, it will be in which one, which mode? When reset equal to 1, it is connected to 0 is connected to this one. That means it is in reset mode. When reset equal to 0, it will be there in which mode? Functional mode. And when reset equal to 1, it will be there in reset mode. This is nothing but synchronous active high reset. Did you understood the circuit diagrams for both these 4 resets?
Yes, sir.
Yeah. This one I will share, don't worry. Yeah. Any doubts or queries in this?